Hello students, welcome back. Now let's go to section 4, subsection 4.3, chi-square distribution. The chi-square distribution is a special case of a gamma distribution. Here, plug in alpha as nu over 2 and beta as b, or beta as 2, excuse me. Then we have this expression. Here, Greek letter nu is called the degree of freedom. It looks kind of like Roman letter V, but what I intended here is Greek letter nu. Now, have you heard about the degree of freedom before? It does appear in chapter 1, but I did not emphasize it at the time because I didn't think students were ready. Now I think people are ready, so let's talk about it. Typically, the degree of freedom is n-1, where n is the sample size. And that's for one sample inference. So if you have 2 or more samples, then we get 2-dimensional, 3-dimensional, we have higher dimensional calculus. In that case, we may end up with n-2 or more complicated degrees of freedom. But let's stick to just one-dimensional case because after all, multivariable calculus is not required for this course, and we're going to stick to, most of the time, one-dimensional example, one sample inference, and even when we do consider 2-sample inference, we consider special cases when they're tied together so that the dimension or calculus stays just single variable. Now, where else did you use this n-1 before? That appeared in sample variance. How do you calculate sample variance? x1 minus the mean, x bar, and this quantity is called the deviation, the distance from the mean, and take the square to make it positive. Do the same thing to the second statistic, x2. Do the same thing for the third statistic, and so on. Add them all up for all sample statistics, all n of them, and take the average by dividing by, not n, but n-1. Why? Because that's the degree of freedom. Originally, x1 through xn could be anything. But then again, I took the mean, so x bar is known. Now therefore, we have an equation, a linear equation, and x bar is known. So that determines one sample statistic, say xn. And xn can be determined by everything else, x1 through xn-1, and then x bar. That'll determine xn. Doesn't have to be xn. x17 can be determined by the other xk's and the mean, and x3 can be determined by the other xk's and the mean. So n-1 of those sample statistics can be anything. They're free, but those n-1 free numbers plus x bar will determine the last sample statistic. That's what this degree of freedom is all about. That's why we're dividing by n-1 here, not by n. And that's not really the whole story of this, but anyway, here we go. In short, this degree of freedom is something we already discussed. Excuse me, we didn't already discuss. I'm talking about this for the first time, but it was discussed in our textbook earlier in chapter 1. It's just that at that time I skipped it because I thought the students weren't ready. Now people are ready, so I'm talking about it now. And that's what the degree of freedom is all about, at least at this level. And with that, we get this gamma expression, and that's called chi-square distribution. Here's an example. Let V be a continuous random variable that follows a chi-square distribution with a degree of freedom nu equals to 14. So according to this, the sample size must be 15. See, n-1 is 14. All right. Estimate the values of chi L squared and chi R squared so that V is less than this quantity. That probability is 5%. V being greater than that quantity is again 5%. Here's a visualization. This red shading is 5% and that corresponds to this. And this green shading corresponds to the second expression here. So 5% here, 5% there. Now, how do you find out those chi L squared and chi R squared? Now, by the way, the reason we do these squares is traditional, and this thing is called chi-square distribution. It comes with square, and it's not coincidence that I'm using V for variance, and then we already used V sample variance for this because they are related. And speaking of sample variance, we all have all those deviations squared, right? So they are really related to squares. All right, let's find out chi L squared and chi R squared. You don't really have to go through this expression and calculate the integral. What we need is chi-square table. Let's open up chi-square table. This is posted in Canvas. All right. Now we have similar picture as saw before, and all these numbers here corresponds to the right-hand side shading. Please recall the normal picture had left-hand side shading. So those values were CDF values. Here it's reversed. It's right-hand side shading we are looking at. Let's go ahead. But here, this is right-hand side shading, green, but this one is left-hand side shading. So this one is 5% all right-hand side. This one, we need some work. 5% to the left, so this one is associated to 95% to the right. So 5% here means 95% there. Make sense? So red is associated to 95%, green is associated to 5%. Let's go to the table again. Here, chi-squared 0.95, that's associated to 95%, so it should be around here, so that big chunk is 95%. And now here, chi-squared of 0.050, that's 5%. So around here, so that right-hand side is 5%. And then let's scroll down further, and degree of freedom of 14. That's what we are looking for. Let me go to a little bit bigger window. So we have this picture. And then, so degree of freedom of 14. And then I'm looking for 5%. So you see, this shading here is 5%. So chi-square value I'm looking for is 23.685. On the other hand, this one, the left-hand side, so that this shaded right-hand side is 95%, that's associated to 6.571. So those are chi-square values. Chi-L squared is 6.571. Chi-R squared is 23.685. All right, so that's how you can find chi values. All right, let's go back to my Mathematica notebook. The solution, yeah, this part 5% and that part 95%, that corresponds to 6.571. Here I did a little bit more accurately using Mathematica, 6.57063. And right-hand side, chi-R squared is 23.685. Look at this. 23.6848, yes. So those are the chi-square values that I was looking for. So this value here, 6.571, this value here, 23.685. Go back to table, and 23.685, 6.571. If you choose different degrees of freedom, then you can choose different row. If you use different percentages, then you can use different columns. That's how chi-square distribution table works. That was easy, wasn't it? By the way, why is this so important? Because chi-square distribution is related to the distribution of sample variance. Same chi-squared, and then variance, this is degree of freedom, and then sigma squared is population variance, and this is going to be fixed. And then this is sample size. That'll change depending upon what sample size you take. So what do we have? This sample variance is proportional to chi-squared. Sample variance is proportional to chi-squared for the right degrees of freedom. That's the motivation, and that's why chi-squared is important. And of course, the most important part was not the gamma expression or integration, but how to look at the table, how to work with the table, basically. That's the most important part.